morning. How you doing? How you doing today? Who we got here? Let's see, we got one person on Zoom and a couple of people on YouTube. It's good to see you. Are you having a good Wednesday?
A wonderful Wednesday.
Oh, good.
Great. I went mountain biking for the first time yesterday.
Oh, nice. And it's going to be hot today.
Yeah, it's going to be a lot warmer than it was yesterday.
Yeah, like 85 or something, and then tomorrow 90.
No.
Yeah,
and I haven't checked it what tomorrow is.
Friday like 93 or something.
Oh no, that's really hot. Okay, but next week is a lot cooler. Next week, 77, 71, 62, 67, 70 off.
Oh, I see the updated now. Today 87, tomorrow 91, and then Friday 90.
Yikes.
But then, yeah, we drop down again next week to something more reasonable. But I had to put on a sweatshirt this morning because it's a little chilly.
What?
But I know it's going to change.
It's basically summer already.
I know. What do we have? We have winter, which this year went by really quick. It's just December. Boom, that was it. And then spring and then summer.
We didn't even have a rainy season at all.
Oh, yeah, we had 1 month of rain and that was it.
Summer's gonna be bad. I hope it doesn't get too bad with the forest fires, but...
Oh, yeah. I already stocked up on masks, as I figured. There was one summer, a couple of years ago, the smoke was just really bad.
Yeah,
in fact,
I remember driving home at night, and the smoke was like just dense fog. Like,
yeah.
It was so hard to see.
Yeah. You probably weren't around a few years ago, but they actually closed our campus for a couple of days one year. Smoke was so bad.
Oh, was that 2018 or 17?
18 sounds all right.
I remember.
It's funny, I think of that not being very long ago. Part of that's because the last 2 years have just been all that, like, compressed into one weird, hazy. It's hard to kind of judge the passage of time over the past couple of years.
There hasn't been many events. I think events are the things that, like, give you, like, oh, okay, time has passed. I can remember an event, and that was before, like, 4 other events that I've, like, done.
Yeah.
Like, you don't have anything to, like, mark the calendar with. It just turns into a blur.
Yeah. Well, today we're going to cover 2 graph algorithms. We're going to do spanning tree, which we actually did a little bit of last time, and then we're going to cover shortest path, which is used by mapping applications to get you from your start to your destination. And then also show you how that shortest path can be used to resize images in a very interesting way. So,
I also saw we had Dijkstra's algorithm.
Yep.
What is that?
That's the shortest path one. So Dijkstra is the
one. It's just a different name.
Dijkstra. Well, it's pronounced Dijkstra. The J is kind of silent. That's,
okay.
I think it's a Polish name. And so he was a computer scientist and mathematician who came up with this algorithm. And Prim was the one that came up with this spanning tree algorithm.
That kind of explains where it like had the name.
Yeah.
Because Witcher has what's it called? A character named after the computer science guy that made that algorithm, and Witcher was made by a Polish game studio.
Ah.
So of course they used a Polish computer scientist.
Yeah.
Smart.
So this was the graph that we came up with last time. If you remember, I had a picture of like a little kids town with some stone paths between them, but then we can just turn that into a graph by putting a vertex where each house was, and then an edge where each path was, and then put in a weight which represents the number of paving units that were required to pave that particular path. So this picture here is a more abstract, general form of that graph. So let's just go over kind of informally how you would go about computing the minimal spanning tree. Now I want to put emphasis here on the word tree. The tree means that what you're going to get is a graph that has basically a root and then branches coming off of it. It's not necessarily going to be a continuous path through the graph. It's probably going to have two or more branches, although it doesn't have to. But a tree means there's never going to be any cycles. For example, if we had put this edge and this edge into the tree, we would then not have to put this third one in. That would create a cycle and would also create a redundant edge that we don't need. So the whole purpose of this minimal spanning tree is just to hit all of the vertices, but we won't necessarily use all the edges. In fact, we definitely won't use all the edges in this case. So the way we do this is we just pick a vertex to start at. Now, if you're a computer, you're probably either going to pick randomly, although random is a little difficult to do. You might just do something like pick the first vertex in your list of vertices. And so in this case, it's just A. So we could just start there. We're going to hit all of the vertices, so it doesn't matter where we start. And then you look at all of the edges that are coming out of the vertices that you've visited so far. In this case, it's just A. So we're going to look at the 3 edges that come out of A. And the weights are 4, 3, and 5. And then we just pick the lowest one, which is this one going to C. And then we just repeat the process over again. But this time, we look at all of the edges coming out of all of the vertices that we've included so far. So we've included A and C, so we're going to look at all the edges coming out of those two. And we're also not going to include any edges that go back to vertices that we've already included. So we're going to look at this 5, this 3, this 3, this 4, this 5, and this 4. Those are all the edges that we're going to consider. And then you just look at the weights and then pick the lowest one. If there's a tie, then you just break the tie either randomly or, pick the first vertex in your list. So it looks like we do have a tie. We get a tie between this 3 and this 3. So just either pick randomly or pick the first vertex on your list, which would be B, just because it alphabetically comes before F. And then we just continue doing this over and over again until we have included all of the vertices in our tree. So we're going to look at all the edges coming out of all of the vertices that have been included so far. So we're coming out of A, coming out of C, and coming out of B. But we're not going to look at that edge across the top between A and B because we've already included both A and B in the tree. So that edge across the top, even though it has a weight of 5, which is higher than all the others, we're not going to include it because it goes between 2 vertices that we've already visited. Okay, so we look at the lowest one. I think the lowest one is going to be this 2 right here. So we'll go along that edge and reach F, and then we just continue again. So we look at this edge, this one, this one, this one, this one, this one, this one, and this one. Kind of see we have this ever-expanding, sort of like what you might call it, what graph theorists call a frontier. So the frontier is kind of this edge, this path that's expanding through the graph, and we're expanding our search area a little bit more each time. So we look for the lowest one. So we've got a 4, a 5, a 4, a 4, a 3, a 3, and a 3. So there's 3 3s. So we just pick the lowest one, and if there's a tie, pick randomly. I'll just go to D here. And then repeat again. Look at all the edges that are coming out of all of those vertices. Pick the lowest one, which I think is this 2. and then repeat. Looks like it's going to be this 3 right here. And then repeat. Oh, let me trace those again. Okay, looks like there's a 2. And then repeat. Let's see, this way, and this way. We got 2 3s to consider. So let's just pick the one that comes alphabetically first, which is going to be I. Oh, actually, we're going to I in either case. I guess we'll come out of G because that one's earlier alphabetically. And then one more to do. So we'll look here, 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 and here. And then we've got a 2. So let's go that way. And so now that we've touched all the vertices, we're done. And if we kind of imagine taking these, this graph and picking it up by one of the vertices. Let's say we pick it up by A. Then it goes to C, and then there it goes to B. And B branches to D and F. D goes to H, F goes to J, J goes to G, G goes to I, and then I goes to E. So you can see this tree structure, although it's not a very interesting tree. And then if we were to add up all the weights, 3 here, 3, 3, 2, 2, 3, 2, 3, and 2. If we add that all up, I believe we come up with a total of 23. So no matter which vertex you start at, you'll end up with the same minimal weight. So it's a pretty easy algorithm to do. This is called a greedy algorithm. In a greedy algorithm, the algorithm goes stepwise through the process of solving the problem, and then every time there's a decision to make, and here the decision to make is which edge are we going to select next. Every time there's a decision to make, it picks the best one. So one thing a human might do in order to evaluate which edge is the best one, the human might like look ahead and go, okay, well, I'll pick this one because the next vertex will maybe have more choices available to me. Or maybe I'll pick this one because I can see that later on that's going to result in a better solution than some other one. But a greedy algorithm doesn't do that. A greedy algorithm doesn't look ahead to see what choices will come later. It only looks at the information that it has available right now. Remember when we were drawing these edges out here as this expanding frontier, those are the only things it considers. If it looks at these sets of edges here, it doesn't then go and look at this one or this one. It just looks only at the edges that it's supposed to look at that moment and then picks the best one. So I'll say here, pick the best one based only on the immediate information. And the second thing a greedy algorithm doesn't do is it doesn't change its mind later on. It doesn't go through the algorithm and go, oh, actually, it turns out that wasn't such a good choice. I should back up and change my mind. So as we went through this spanning tree algorithm, we just looked at the available edges, that were coming out of the vertices that we had already included in the tree, and then we just picked the best one. I mean, just really kind of just like go through all the edges, sort them by weight, and then find the lowest one. That's all you got to do. At no point during the algorithm did we go, you know, that wasn't such a good choice. We should go back and switch it to a different one. So a greedy algorithm makes a decision and then sticks to it. That's opposed to a backtracking algorithm, which does occasionally go back and change its mind. So it might explore one branch, kind of like solving a maze, right? If you're solving a maze, you might go down one branch of the maze and realize, oh, that was a dead end. I need to back up and then try a different branch. That's a backtracking algorithm. But a greedy algorithm looks at the available information, makes a decision, and sticks with it, and then moves on to the next step. So up here in the corner is a more formal, but still somewhat informal description of how the spanning tree algorithm works. And also, we can do this algorithm not with the actual circles and lines, but by representing the graph as a matrix. Here's that same graph with the same 10 vertices and the same edges, and you can see that the weights have been put in this center section. So there is an edge between A and B with a weight of 5. And there's an edge between E and F with a weight of 4. So what we're going to do with this is use this matrix in order to do that same algorithm, but without the picture. Give me a moment here to bring something up on my screen. All right. So we'll say that these vertices on the left-hand side of the diagram represent our visited vertices, the ones that we have included in the tree so far. And the ones across the top are our unvisited vertices that have not been included in the graph yet. So step number 1 says initialize the set of visited vertices with any vertex from the graph. So we just look at this list and we just pick one. Now, if you're a computer, you're probably just going to pick the first one off the list. So let's go ahead and let's highlight this row, which indicates that this is the vertex that we have chosen. And we're also highlighting it to show which edges we're going to be, which edges come out of that vertex. Let me catch up on the comments here. So the first comment was, how did I number these paths? That was in this one here. So there was a picture that I had here originally that had houses and some paths between them. And so the numbers represented how far the houses apart were, how far apart the houses were. So house A and B are 5 units of distance apart, whatever that unit is. And house A and C are 3 units apart, whatever that distance is. So that's where those numbers come from. Does the minimal spanning tree algorithm provide a solution for the traveling salesman problem? No, this is not the traveling salesman problem. Traveling salesman problem is a different one. That's one where you want to make a circuit through the graph. So you want to start here and then find some path that goes through the entire graph and then comes back to its starting point. And the goal of that one is to find the shortest circuit. You've got to go through all the vertices and find the shortest one. So that's a different problem. Okay, so back to this one here. Initialize a set of visited vertices with any vertex from the graph. So we have picked A. And then initialize the set of unvisited vertices to all but the starting vertex. So we're going to go through our list here and take away A. So we're going to cross this one out. And the way I'm going to cross it out is I'm just going to cross out the entire column that A is on. Okay, so I've essentially added A to this list of vertices, and I've removed it from the unvisited list. Step number 2, consider each of the unvisited neighbors of the visited set. So my visited set is just A right now. Here are the unvisited neighbors, B, D, and E. Identify the neighbor with the lowest weight. So we look at all of the highlighted edges, 5, 3, and 4, and then we pick the lowest one, which is this 3 right here. So I'm going to go ahead and circle that one. So by picking 3, it means that I have now decided to go to node or vertex D. So I am now going to highlight the D row as well and simultaneously cross it out. Okay, so I have now included D in the visited set, and I have removed it from the unvisited set. That's what step 4 is. Add this neighbor to the visited set and remove it from the unvisited set. And then go back to step number 2. So step number 2 is consider each of the unvisited neighbors in the visited set. So we're going to look at all of the edges that are highlighted and then pick the lowest one. And again, if there's a tie, you just break it randomly or pick the first one off the list. So it looks like there's 2 3s. We'll break that tie by going to B, because it's just first on the list. Okay, so we just repeat. We've now decided to go to B, so I'll highlight that row and I'll cross it off. And then look at all of the highlighted edges. And then pick the lowest one. There's a 2 right here, so we should select that one. So that means we chose to go to I, so I'll highlight that and cross it off. So remember, we're highlighting and crossing off because we're going to add this neighbor to the visited set, and we're going to remove it from the unvisited set. So by highlighting that row, I've added it to the set of visited, and by crossing it off vertically, I've removed it from the unvisited set. And then look at all of the highlighted numbers. Pick the lowest one. Looks like there's 3 3s, so I'll pick the one that comes first. Right here. So that means we're going to C and crossing it off. All right, keep going. Circle, circle, this one, here, here, and here. Pick the lowest one, which I think is going to be this 2. So that means we're now going to go to J. Oh, I forgot to circle it. And cross off J. And then again, look at all the highlighted numbers. Pick the lowest one, which is this 3 right here. Circle that. That means we're going to H. Highlight H. Cross it off. And then pick the lowest one, which is this 2. So that means we're going to F. So highlight F and cross it off. And then again, look at all the highlighted numbers. I think that's it. Pick the lowest one, which is this 3 right here. This is just a repetitive process. Remember, every time we look at the list of available edges, we just find the lowest one, pick it, and then we're at no point are we changing our mind about which one we pick. Okay, so we're down to the last few of them. So there's only this 2 here. So that means we're going to E, and then finally we cross off E. And now we reach this last step. If the unvisited set is empty, we are done. So the unvisited set has now had everything removed from it, and so we are finished. And then we can just read the solution off of this matrix. If we started here at A, we can see we go to D with a weight of 3. And then from D, we go to B with a weight of 3. And then from B, we go to C and I with 3 and 2. And then from C, we go to J with a weight of 2. And on J, nothing is circled, so that's the end of the line for this branch. From I, we go to H with a weight of 3. And then from H, we go to F with a weight of 2. From F, we go to G with a weight of 3. And from G, we go to E with a weight of 2. And then E doesn't have anything highlighted on it, so that's the end of the line for that branch. And then again, if we were to add up all of those weights, we would get 23. Okay, so that's Prim's minimal spanning tree algorithm. And so minimal spanning tree gets used for applications like, well, not so much for paving roads. I mean, that's really, it was kind of like a contrived example. But one example is in computer networks. So you have a typical network. You probably have a small computer network at home. You've got your internet service provider that's providing your connection to the greater internet. And then within your home or office, you probably have a router. And then maybe some other switches scattered around the house with connections going between them. You've got wireless connections going to tablets, laptops, phones. And then maybe you also have some wired connections going to televisions, other computers. And this is, roughly what my home network looks like. So you've got a mixture of wired and wireless connections in there. But even though you have wireless connections here, they're still considered by the network to be a direct connection, almost like they're wired in. And so your network works fine as long as there is this tree structure or this star structure. Actually, I could describe it as a tree, right? So this is the root of the tree. This is your, I don't know, in America we call this the router, but I guess elsewhere it calls it a router. But basically it's a tree structure, right? You can see the tree structure here. And so the network works fine as long as you do that. But have you ever, and I'm going to ask you, have you ever created a cycle in your network? Like created an extra connection between two switches? Has that ever happened to you? Did you ever accidentally do that? Now, it's kind of difficult to do that, but if you're in a larger network, like let's say one in an office building, it might be easier to do that just because, you've got cables snaking through walls and through ceilings, and it can be kind of difficult to tell what goes where unless you're labeling them really well. And so you might accidentally connect two switches together and create a cycle in the network. So what happens there? What happens when you create that cycle in the network? Well, what happens is sort of dependent upon how much you spent for your networking equipment. If you bought, pretty much standard consumer networking equipment, then one of two things will happen. Either those switches will just go crazy, and as data comes in and it has to be sent over to, let's say, this computer here, what this switch does is it has to memorize, where are the various things in the network, and they're learned by their what's called their MAC address. The MAC stands for Media Access Control. And so every device on your network has this unique 48-bit identifier that is, like I said, unique in your network. And so every switch is learning where every device is. And so this switch over here, will learn the MAC addresses of all these things, and MAC addresses of all these, and MAC addresses of all these. And so when this data comes in, and let's say it's bound for here, well, what will happen is, even though it might go here, what also might happen is that the data will just like swirl around this network as each one of the devices hands it off to the next one that thinks that it has the path to that particular destination. So the data will just like swirl around, and you'll see the activity lights on that switch just light up and go solid as the data just creates this cycle and goes around and around and around. The other thing that might happen is the switches might realize that this is happening and then just completely shut itself off. So this switch basically will say like, this is crazy, and it will just like either disable that particular port, or it will just shut itself off, and then your whole network basically dies at that point, as all of those devices think that something has gone majorly wrong with the network, and they all just disable themselves. So that's for your relatively inexpensive consumer networking equipment. Now, if you buy higher-end business-grade equipment, which means you might be spending not $20 or $30 on a switch, but you might be spending $100, $200 on a switch, those are smarter. Those switches will basically try to figure out what's the best way to get all of the switches in our network connected, but so that there's no redundant paths. So these switches, when you connect them up, will start talking to each other, and they'll send information back and forth about which devices are connected to them and how fast they're going. And these switches then will run basically the minimal spanning tree algorithm and figure out how can we connect all the switches in the network and at the same time reduce the overall latency. Latency is how long it takes to send data between one point and another point. Or how can the switches then create the greatest bandwidth, so the greatest speed overall. So they'll start communicating with each other, and they might discover that although there's a redundant connection, this one here should be taken out, or maybe this one should be taken out, or maybe this one should be taken out because one of them is slower than the other. Maybe they're all gigabit connections, but one of them for some reason has fallen back to the 100 megabit speed, and so it decides to take this one out. So the only thing that's important here is that all of the switches and all of the devices are reachable, and the minimal spanning tree is trying to make the network as fast as possible. So you connect up the switches in a redundant way with a cycle in it, and these switches will run the minimal spanning tree algorithm. They literally will, and sometimes if there is a way to look at diagnostic output from them, you can actually see a message that gets printed out in the log file that says running minimal spanning tree. And so these switches start talking to each other, and they figure out how can we create this network so there are no cycles, but the overall speed of the network is as great as possible. And you can even do fancy things, like you can put in not only single redundant connections, but multiple redundant connections. This is called trunking, and the switches will take advantage of that. Now you've essentially got a 2 gigabit per connection, 2 gigabit per second connection running between two switches, because you've got parallel wires running between them. And the advantage there is that if one of these wires gets cut for whatever reason, like a rat eats through it, or in an office environment, it could be somebody, you know, accidentally cuts it, or in a larger multi-office building environment, somebody, you know, accidentally runs a shovel through the wires that are connecting the buildings together. The switches will again run a minimal spanning tree and try to figure out how to route around that problem. So if one of these connections gets cut, they'll run minimal spanning tree. When you cut both of them, then they'll run minimal spanning tree again and figure out how to route around the problem. So basically, every time a device is connected or disconnected from the network, they run this algorithm and figure out how to connect all the devices up and make sure that everything's connected to everything else. It's very cool. So minimal spanning tree is used in computer networking all the time in order to deal with redundant connections, eliminate them where they're not needed, and put them back when they are needed. So, you know, I don't know about you. I go and just buy the cheap switches. Myself, I tend to spend a little bit more on them, just because I want something that's nice and reliable. I don't buy the enterprise grade ones that, you know, deal with this minimal spanning tree, but at least I tend to buy the ones that cost, you know, $80 rather than the ones that cost $20. In most part because, and this is speaking from experience, I want my computer network at home to be the most reliable piece of the puzzle. Like if something's not working, like for some reason, let's say my laptop can't get a connection to the internet, I don't want to be sitting there thinking, well, I wonder if the problem is with the switches, or I wonder if the problem is with the cables. I'd rather think, oh, it's not likely to be the network. It's not likely to be the physical infrastructure. It's more likely to be something going on with that particular device. Or maybe it's something going on with my internet service provider. So I want the network to be like as reliable as possible so that I don't really have to think about or consider that might be the problem. And once in a while it is, but it's something that I explore after I've tried to explore every other possibility that might have gone wrong. You know, that came out of personal experience, and it also came out of, I remember, hasn't happened too recently, but I can remember 15 years ago, 20 years ago, I would know people who would say like, oh yeah, I reboot my router every day. And I'm like, what? Seriously? And they're like, yeah, you know, it just clears up any little problems. It seems like by the end of the day, it's slowing down. So I just reboot it, and then, you know, everything speeds up again. And I'm like, that's crazy, right? I mean, so your router basically is like the least reliable piece of your network, you know, rather than being one of the most reliable ones. And that's what I want personally, is I don't want to think about like, oh, I need to reboot the router. I mean, so again, like I tend to buy, like, if I can, routers that cost a little bit more so that I've got reliability in them, rather than thinking like, oh, I need to reboot the router and see if that fixes the problem. So the tree structure can also be called a daisy chain structure, because you've got, you know, you got one switch that talks to another switch that talks to another one, right? So everything is chained off of each other rather than creating a cycle. You've just got this long chain. Does anybody know why it's called a daisy chain? Like, what does that term mean?
That's what I was about to ask. I was like, do daisies grow in chains, or is it like someone has made a chain of daisies like in the past, and then that's a normal, like, culturally accepted thing?
Oh, it's a good question, right? So, you know, this is what like some kids do, is they literally pick daisies and then they tie them together and make chains. So that's where the term comes from. Does that answer your question?
Yeah, it looks like what's it called? Looks like one of those wreaths that like Greek
Oh yeah, yeah. You know, wear it around your head.
Yeah.
Kind of like that. So that's where that term comes from.
The most surprising term to this day is spam and ham for me. I did not know that spam filters and spam folders are from the fake meat. Well, not fake, kind of.
Well, so that's I'm old enough to have grown up in that era, and I know where that word comes from. Um, Part of it comes from the very first spam messages that were sent out were literally the word spam over and over and over again.
It's like an inside joke. People were like, let's use the email services that costs us literal money and just spend thousands, not spend thousands, send thousands of like just spam, literally just the word spam.
Well, yeah. So the question is like, why'd they choose spam? I mean, other than it's just kind of like a funny word, right? So that comes from a 1970s skit by a troupe called Monty Python.
Oh, of course, it always comes back to Monty Python. Which
Uh,
one is it? Is it the one with knights or no?
no, it's literally called the spam skit.
I'm gonna look this up.
I'm looking it up right now. Here.
Morning. Well, what you got?
Oh, there's no actual video on that one. That's weird.
Also, this might get flagged for copyright.
Oh, I don't know. Maybe.
It is Monty Python, so
No audio?
Morning. Morning. What you got then?
Well, there's egg and bacon, egg, sausage and bacon, egg and spam, egg, bacon and spam, egg, bacon, sausage and spam, spam, bacon, sausage and spam, spam, egg, spam, spam, bacon and spam, 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 egg and spam, 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 baked beans, spam, spam, spam and spam. Oh, lobster thermidor crevettes with Mornay sauce, garnished with truffle pate brandy and a pie on top and spam. Have you got anything without spam in it? Well, spam, egg, sausage and spam. There's not got much spam in it. I don't want any spam.
Why can't you have egg, bacon, spam and sausage?
That's got spam in it.
Not as much as spam, egg, sausage and spam.
Look, could I have egg, bacon, spam and sausage without the spam? Ugh. What do you mean? I don't like spam.
So, there you go.
that explains so much.
So-
It's such little term.
So people would post messages on these discussion boards and just fill up the screen with the word spam over and over again, thousands of them, and then post that message over and over again. They're basically just, I think they're just copying and pasting, right, the word spam over and over again. And the whole point was to fill up the entire discussion board with messages consisting of nothing but the word spam.
The word spam, which
Yeah.
is like now a technical word in like email and everything, came
Yeah.
from an internet meme that came from a British style SNL skit, basically.
Yes.
That is so convoluted and funny. Oh.
So to spam someone or to spam a discussion board basically means
was
to
literally fill it
up.
with the word spam.
Yeah, initially it was to fill it up with the word spam, but it evolved into just to fill it up with nonsense. So, it didn't have to be the word spam. Eventually it turned into other words or other phrases, but to spam someone or to spam a bulletin board was to mean to fill it up with just gobbledygook nonsense. And then that evolved into the unwanted email that we started getting around that time as well. And then the Hormel company that actually manufactures spam got into the fray because they said, well, spam is like a copyrighted word. That's our trademark. You can't use that word. And so I went to court. Basically, Hormel was saying, you can't use that word to mean, what it isn't because it's our trademark. And the court said, well, it's too late. The word has entered the common popular vocabulary, And so they reached a decision that said that as long as spam was not capitalized, then it could be used to mean unwanted emails. And as long as it was capitalized, then it was their trademark. That's the agreement that they reached. They basically said, so if you're going to talk about the spiced ham canned product, use a capital letter. And if you're going to talk about unwanted emails, then use lowercase letter. So spam has now become a generic term that just means unwanted messages or unwanted email. How's that for internet history?
It's so much.
People on YouTube like didn't know that. Yep, that is. I mean, I personally witnessed those messages. I saw them. Like I would back then in the 1980s. You didn't have Discord, but you had things like that. You had what are called bulletin board systems, which could be used to chat with each other and send messages.
Were those based on telephone networks? I
Yeah.
remember seeing a couple videos on them. So like you would just call someone basically, and that would like get into their server. In a
Yeah,
way?
with your computer, you would call them with a modem that would send those tones across the phone line, and that would.
Interesting.
Oh,
And you could share
I'll
a lot
show
of it
you
would be
sometime.
share information and stuff. Wait, isn't there like I'm watching this one channel called like I forgot LGR? No, it was a different one. It was he had like an old like 80s computer, and there's like a newer chip that you can buy that would let you use bulletin boards but connect it to the internet instead of connected to a telephone line. So you can still like have the 80s experience of using bulletin boards, but without having to use a modem and a telephone line and everyone's still connected.
Because you can hardly get these telephone lines anymore that work with old style modems. But yeah, there's still a handful of these bulletin board systems being run. You get them, like you said, you access them over the internet now. But yeah, you can get this little device that basically plugs into the back of your old 80s computer, like one of the ones I got in the background here. And then instead of dialing a phone number, you dial an internet address. And then dial, meaning like you type in a command that says, make a connection to, 10.12.5.2. And then it connects you with the server on the other end. And then you get that 80s text-only bulletin board system experience. And so they still exist. They're still out there. But I remember dialing into those things and then just seeing pages of the word spam scroll by and just being totally annoyed that I couldn't see the regular messages. And back then, disk space was limited. A lot of these bulletin board systems ran off of floppy disk drives rather than hard disk drives. And so the entire message database could be just a few hundred kilobytes. And so it wouldn't take long for someone to just post a bunch of messages that would cause the real messages to be cycled off of the database, and then the entire discussion board be nothing but the word spam. I mean, literally, that's all the messages you saw. You know what I mean? Like, you could only, let's say you can only hold 200 messages total. That's a low number, but let's say you can only hold 200 messages total. So as older messages reach that limit, they would just be deleted, and the new messages coming in would then fill up the slots. Imagine an array that can only hold 200 slots, and so the ones that reach the end just get cycled off, and the new ones get pushed onto the other end. And so these spam messages would just fill up all the available slots, and then all the other messages would be gone. So even if the system administrator or the moderator went in and deleted all the spam messages, then the old messages, the real ones, would no longer exist. And so you'd end up with just an empty discussion board with nothing in it. So it was super annoying, but also for a while like somewhat funny because it's the word spam over and over again. So let's talk a little bit about how to represent graphs. This was discussed actually a little bit in that video that we saw last time, but I'll just go over it again. So I got 3 ways to represent a graph. One that we've already seen is as a matrix or a 2-dimensional array. So this graph here could be represented with the vertices down the side and across the top, and then inside the the matrix, for an unweighted graph, you put some kind of indication that those vertices are connected. And for a weighted, and especially a directional graph, you put the weights in there so that you know which vertices are connected and in which direction. So let's say for the top one here, you might just put, I don't know, ones and zeros to represent there's a connection or there isn't a connection. So A is connected to B, A is connected to C. I'm not going to put the zeros in because they're kind of implied. B is connected to D and A. C is connected to E and A and D. And D is connected to B and C. You get the idea, right? You put in ones and zeros to represent the connections. And then for the graph down below, we're going to put in the weights. So we can see that V is connected to X with a weight of 3. And W is connected to X, also with a weight of 3. And let's see, X is connected to Z with a weight of 6. And Y is connected to V with a weight of 2, and W with a weight of 5, and Z with a weight of 2. And then finally, Z is connected to Y with a weight of 1, right? So you fill in the interior of the matrix with the weights or just with ones and zeros indicating a connection. You've also got an adjacency list. This one here is basically an array of lists or an array of sets. So you've got all your vertices, A, B, C, D, E, and F. So this is one array. And then each one of those elements points to another array or another set. So A here goes to B and C, and B goes to, let's see, A and D. C goes to A, D, and E. Right, get the idea? And then for the graph down below, now you have to represent not only which vertex is it connected to, but also by what weight. The whole point of these representations is to capture all of the information that's in the graph, so that if somebody were to get one of these representations, they could reproduce that graph. So here we're putting in pairs of values to represent which vertex are they connected to and by what weight. And then finally, you could also represent a graph by just listing out all the edges and all the vertices. So we might say vertices is A, B, C, D, and E, and F. And the edges are the set AB, AC, BA, BD, CA, whoops, CD, and so forth. And then for the graph down below, you just have to capture those connections also with their weights. So we've got A going to B, oh, not A going to B, what am I doing there? V going to X with a weight of 3, and W going to X with a weight of 3, X going to Z with a weight of 6, and so forth. So again, the whole point is just to capture all the information that's in the graph so that you can reproduce the graph if you have the representation, or you can turn the graph into a representation. So all of these have their uses. The nice thing about the two-dimensional array is that nearly every programming language supports this kind of data structure. You can have a two-dimensional array and then fill in those values with numbers or letters or whatever you need to represent the information in the graph. The problem with the two-dimensional array is that for many graphs, particularly ones that have a lot of vertices, it tends to be rather sparse, right? A lot of open empty spaces. So you end up using a lot of memory, but not necessarily a lot of it being useful information. A lot of it is just going to be empty space. The adjacency list is nice because many programming languages, but not all of them, many programming languages have some kind of data structure that supports this kind of structure. It might be called an associative array, it might be called a dictionary, a hash map or a hash set, something like that, where you can basically use the key being not just a number, but a letter or a string, and then the value being this list of other vertices. So Python supports this kind of data structure, Java does, but C not so much, because C pretty much just has arrays. And then if your programming language supports lists or sets, then this one here can work as well for you. The nice thing about the adjacency list or the set of edges and vertices is it's a condensed, nice, compact way of representing the graph. There's no wasted space. There's no representing things that don't exist in the graph, whereas the two-dimensional one here has lots of like empty spaces to represent things that aren't in the graph. So you should pick a data structure that kind of depends upon what algorithm you're running. So some algorithms lend themselves better to using a two-dimensional structure. Some of them lend themselves better to using an adjacency list. You just kind of have to analyze the problem and figure out which one's going to work for you. Okay, so that's kind of it for minimal spanning tree. Let me catch up on some of the comments here. So the question is, what is broadband meaning? Oh, I don't really like that term, broadband, but basically it means a relatively high-speed internet connection. And these days, at least in the United States, we're wrestling over what does high speed mean? Like what's a minimum speed to be able to be a reasonable internet connection these days? And I think not the courts, but the legislature has said like a minimal speed that's reasonable these days is like 15 megabits download speed and an upload speed of like, I don't know, 2 or 3 or 4. You know, as far as just being absolute minimum, of course we'd want more, right? But as far as being like, this is the minimum speed that one person needs to be like to get a useful experience out of the internet. It's fast enough to do streaming of video. It's fast enough to do downloading of files of reasonable size. Of course, 15 is like, we would think ourselves like, that's not fast enough, but that would be like minimum. And the reason why they're wrestling with this is because we're getting to the point where we considered internet to be almost like a necessity, not a luxury, like it has been. And if it's a necessity, like electricity and water and what else, like sewers, then there ought to be some initiatives to make sure that every citizen, everyone who owns a home has access to at least this minimum speed of internet. And so they call that broadband. I'm not exactly sure why it's called that. Like I said, I don't think it's a really useful term that describes what it is. You can't figure out what broadband is by just analyzing the letters or the words within it. And then what does ISP stands for? ISP stands for Internet Service Provider. That's who you get your internet service from. You know, it could be a local phone company, it could be a cable television company, it could be a satellite dish company, but like, who do you pay to get your internet service from? For some people, it may just be like, you know, your phone, whoever your phone provider is that's how you get your internet. So that would be your internet service provider. Oh, in India, network speed is 30 megabits per minute per second minimum. Wow, that's pretty impressive. So the problem here in the United States is that almost all the internet service providers are private companies, and private companies, of course, want to make a profit, and so they are incentivized to basically provide the minimal service for the maximal fee. And for people in urban areas, that's not necessarily a problem, because the internet service providers come into a neighborhood, they drop off equipment in, you know, strategic places, and then from there you can send the wires out to people's homes. So in an urban environment, a city environment, that's easy to do, because you can drop one piece of networking gear at, let's say, a neighborhood intersection, a road intersection, and then branch out your wires from there to reach all the homes in that neighborhood. But in a rural area where the houses are spread far apart, some of the rural areas in the United States have homes that are a mile apart, it doesn't make financial sense for an internet service provider to drop one piece of equipment, expensive piece of equipment, like per home, because the wires just simply can't go that far to reach the other homes. And so these internet service providers will say, like, why should we put $50,000 worth of equipment to service basically one home, and then put another $50,000 piece of equipment to service another home, and then dig all the trenches to service those? And so there's kind of this wrestling that's been going on to, should we force internet service providers to provide service to these rural areas the same way the Postal Service provides mail service to rural areas regardless of the cost? I don't know if you knew this, but there's actually a post office at the bottom of the Grand Canyon, right? They get daily mail service, and it's brought in by pack mule, right? It's hugely expensive to send mail down to the bottom of the Grand Canyon, but there it is, and they're required by law to provide that service. Internet service providers, being run by private companies, don't necessarily have that requirement. You don't have to provide internet service to everyone. And so that's what they're wrestling with. Like, should that be a requirement? Should we require internet service providers to give internet service to everyone and provide at least a minimum speed? Yeah, so now there's something like Starlink, which would hopefully drive down some of the cost and provide more availability. You know, so that, I think, helps a little bit. Okay, let's take a moment here to talk about another algorithm. This is the shortest path algorithm. So this one's a little bit more complicated, but it's used probably millions of times a day to find the shortest path between a starting point and an ending point. So you think about Google Maps or Apple Maps or any of your mapping applications. You've got your starting point, you've got an ending point, and just in a fraction of a second, it can come up with a route between the start and the end. And of course, for a road map the size of the world, this is a very complex problem to solve. But here's essentially how it works. So you've got this, hold on, I need to bring up my notes for this one as well to make sure I'm doing this correctly. I'm going to find my notes. Where did it go? Here they are. So let's say I want to get from A to E. Now this is a really small network, so it's pretty obvious how to do it. But let's say we're a computer and we don't know this. So we want to go from A to E. So wow, there's a lot of stuff here. But it starts out and it says, assign to every vertex a tentative distance value. Set it to 0 for our initial vertex, which is A, and set it to infinity for all other vertices. So we're going to assign to each vertex here a number which represents how far it is to get from A to that other vertex. And initially we don't know the answer, so we're going to set all of those to infinity or just some really big number. But for A, our starting vertex is 0 because we know it takes 0 units of time or 0 distance to get from A to A. Next, set the initial vertex as called current, the current vertex. I'm going to represent that with an arrow pointing to that one. So this is our current vertex. Create a set of unvisited vertices called the unvisited set, consisting of all the vertices except the initial one. So that's these here. C, D, B, and E. Okay, for the current vertex, consider all of its unvisited neighbors and calculate their tentative distance. Okay, so we're going to look at, here's our current one, we're going to look at this edge and this edge. Here's an unvisited neighbor and here's an unvisited neighbor. We're going to update that number that we're storing on each vertex with a distance that we've just learned. Okay, here's how it works. So let's look at this edge here. So now we know that the distance from A to C is 9. So we can update this number. It's not infinity anymore, it's 9. And we're also going to record what vertex we came from. So that's A there. So we know that to get from A to C, there's a distance of 9. Okay, so that's this description right here. And then we'll also look at this edge, and we're going to update that number. This is going to be 4, also from A. So we've just now learned that we can get from A to C in a distance of 9, and we can get from A to D in a distance of 4. And now we can mark this vertex as being done. It's now visited, it's complete, and we don't need to know any more information about it. So that was when we are done considering all the neighbors of the current vertex, mark the current vertex as visited. That's what we just did. Done. And remove it from the unvisited set. A visited vertex will never be checked again. Okay? Now, set the unvisited vertex marked with the smallest tentative distance as being the next current vertex. So we're going to look at all of these numbers, and we'll just pick the smallest one. That's the 4. So this becomes our new current vertex. And then we repeat the process. For the current vertex, look at all the unvisited neighbors, calculate the new tentative distance, and then update the numbers. So let's take a look. So first of all, we're not going to go back this way because that heads back towards A, which is already done. So the only other path to consider is this one. Okay, so we're going to take the 4, we're going to add it to the 3. We get a total of 7, and 7 is better than the 9. We had 9 before, but now we've got a new path that can take us to C that's better than the 9. So we're going to update that number. We're going to change this to 7 from D. So it's not going to be 3 from D. It's going to be 7, which is the total distance it takes to get from A to C. Okay? So what you do is you take the distance to the current vertex, you add on the weight of the edge that you're considering, that becomes your new sum, your new total, and then you see if that's better than the number you had there before, and if it is, you replace it. Okay, so this vertex is now done because we have considered all of the unvisited neighbors. We considered this one and this one. There's no more to do, so that one's now done. Look at all these numbers, pick the lowest one, which is the 7 here, and that becomes our new current vertex. And then look at all the unvisited neighbors, and then update the numbers. So we've got 7 here, We're going to add it to the 4. That gives a total of 11, and that's better than infinity. So we'll replace that infinity with 11, and we're coming from C. And then down here, take the 7, add it to the 9. That gives us 16, and that's better than infinity. So we'll replace that with 16 coming from C. And now this vertex is done. So this algorithm is slowly exploring the graph. Again, it's got a frontier that's going out and trying to find the shortest path. And eventually it's going to hit our destination. Now we've already gotten to our destination, but we haven't marked it as being done yet. So we better finish up this algorithm. All right, look at these numbers. Pick the lowest one. That becomes our new current vertex. And then go along the path and see if that sum comes out to be better than what we have so far. We've got 11 plus 4. We add those together, we get 15, and that's better than 16. So we're going to update this with 15 from B. And then this vertex is done. And then, of course, also E is now done because it has no more unvisited. So we are now finished. Okay, so what do we end up with? We ended up with, now the way to figure out the shortest path is now you work backwards. You go E came from B with a weight of 4, and B came from C with a weight of 4, and C came from D with a weight of 3, and D came from A with a weight of 4. And that's our shortest path through the graph. So it's not like the one with the fewest number of links. It is, in fact, the one with the lowest weight overall. Okay, whew. But that's how this algorithm works. There, let me show you another one. Here's another graph. We want to go from A to H. I'll just run this through as quickly as I can. So we've got 0, infinity, 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 all over the place. And we want to go from A to H. So we want to end up here. Let's mark this as our start and our end. All right, so this is our current vertex. We're going to look at all the unvisited neighbors, which is to B and E, and then we're going to update those numbers. So this is 6A, and this is 2A. And now this one is done. I'm going to cross it off. Our new current one is E because that has the lowest number, 2. Then we're going to look at all of the unvisited neighbors. Not going to go back to A because we already have done that one. So we're going to go to F and I, and we're going to update the numbers. So for F, it's going to be 2 plus 3. This is going to be 5 from E. And then this one down here is going to be 7 from E. Again, the 2 plus 5. And now E is done. And we select our new current vertex, which is the one with the lowest number. That'll be F. So look at all of the unvisited vertices. So we got 5 plus 8, that's 14. That's not better than the 6, so we're not going to change that one. And then 5 plus 4 is 9, which is certainly better than infinity. And then 5 plus 7 is 12. That's better than infinity. And now this one is done. So now look at all the numbers. Pick the lowest one, which is going to be the 7 here. Oh, and actually it's going to be the 6. 6 is the lowest one. So we're going to look at all the unvisited vertices, which is only this direction. 6 plus 6 is 12 from B. And now this one is done. Pick the lowest number, which is 7. That one we can mark at, oh actually no, I was going to say we can mark it as done, but we can't. We're going to go 7 plus 3. 7 plus 3 is 10, and that is better than the 12. So we'll cross this off and put 10i. And now this one is done. So look at the numbers, 12, 9, 10, and a bunch of infinities. The lowest one is 9, so that becomes our new current. Then we go this way. 2 plus 9 is 11. That's better than 12, so we'll update this. Then we'll go this way. 9 plus 6 is 15. And then we'll go this way. 9 plus 6 is also 15. And then G is done. Okay, look at all the numbers. It looks like 10 is the lowest one, so that becomes our new current. And there's nothing to do, right? So there's no other unvisited neighbors of this one, so we can now mark this one as done. Our new current one is going to be C because it has the lowest number. So we're going to go this way. 11 plus 5 is 16. And then C is done. And the reason it's done is because there are no more neighbors to look at. Okay, so now there's 2 vertices here with both with a weight of 15. Let's see, what does it say about that? If the destination vertex has been marked as visited, which it hasn't been yet, or if the smallest tentative distance among the vertices in the unvisited set is infinity, then stop. Okay, so we're not finished yet. So how do we break this tie? I'm not sure. Actually, let's just pick K as being our current one. In part because it's not the. In part because there's a possibility. Well, actually, I guess there's not a possibility. I was going to say there's a possibility that we might find a shorter route to H, but we're not going to find a shorter route. It's going to be at least that long, or it's going to be longer. But let's go ahead and do it anyway. So we're going to update this number here with 15 plus 2, which is 17. And now K is done. And then we find the lowest one, which is H. And then we go this way. 15 plus 3 is 18. That's not better than the 16, so we'll leave that one. And then we'll go this way. 15 plus 5 is 20. That's not better than the 17. So now this one is done. And now at this point we can finish, right? We don't have to look at any of the others. So now we have our shortest path. It started at H, and then going backwards it goes to G, and then from G it goes to F, and then from F, find F on the graph, oh there it is, it goes to E, and then E goes to A. And then if you add up all the weights along that path, which is A to E to F to G to H, then we end up with a total of 15, I believe. So that's essentially how the shortest path algorithm works. And you can imagine for things like Google Maps, this is a huge graph with millions or even billions of vertices and lots of edges. And the edges, the weights on the edges could be ever changing. They might not just be distance, they could also be speed or the time it takes to get from one intersection to another intersection. And you can imagine those numbers are always changing as people who are using the Maps application are feeding information back into the Google servers and updating how long it takes to get from one intersection to another intersection, depending upon how much traffic there is. And that's how Google is able to, or any of the mapping applications are able to dynamically change your route as you're traveling through there, because all those weights are being updated all the time. Although sometimes I do get frustrated with them because their algorithm seems to choose, let's say, the fastest route, even if it's not necessarily the shortest one, or it's not necessarily the one with the least turns. Although now you can usually go into the options and change that. You can say, select the route with the fewest number of turns, or select the route that is the shortest. You know, but sometimes shortest really to a computer can mean, well, this route over here is, let's say, 1.2 miles long, and this other route is 1.21 miles long. So pick the one that's shorter by, you know, 1/100th of a mile. Well, you know, that could mean that there's more turns, or it could mean that you go through a part of town that you don't necessarily want to go through, or you go across roads that are in terrible condition just because you're saving a little bit of distance. And I remember one time, this was probably 10 years ago, I was traveling from here to a destination about 100 miles away, and I had to cross a bridge, a long bridge to get there. A bridge that was about 5 miles long. Now, those of you who live in the area probably know what bridge I'm talking about. And when I got to the other side of the bridge, after paying the toll, which I think at the time was like $3, it told me to, go through some streets, and then basically the route took me back onto the bridge. And once you get onto the bridge, you can't get off of it. There's no place to turn around. So there I was, I'd gone across the bridge, paid the toll, and then it had me go back onto the bridge and go back to the other side. Well, once I'm on the bridge, I'm stuck. So I have to go back to the other side, somehow make a turn around again, and get back on the bridge, going back over again, pay the toll again, by the way. So I paid the toll twice to go over the bridge 3 times. And then finally, when I got to the other side of the bridge, I said, I'm going to ignore the map's directions, and I'm going to just like point my car in the rough direction of where my destination is, and then hopefully the maps will figure out that I'm not supposed to go over the bridge again. And in fact, it did. It rerouted, you know how it recalculates your route if you make a turn that it didn't expect. So I just kind of like pointed in the direction that I knew the destination was going to be in, got it to recalculate the route, pointed toward my direct destination, and then I got there. But I was really kind of mad at that point that I had to pay twice to go across this route and an extra 10 miles of traveling. I was like, I'm going to write to Google, I'm going to demand my money back. I talked to my friend who works at Google. He goes, no, they're not going to, but please report that as a problem, and they'll fix that. He says those things happen every once in a while, that the mapping application just gets confused about where you are, or gets confused about what roads you've been on, and suggests you go back the way you came. Just, I don't know why it happens. It just happens once in a while. But I've never actually had that happen again since then. So that's probably good. Will more nodes in the network increase ping time? Yeah, it usually does, because the ping time, the amount of time it takes data to travel across the network, is based pretty much on the distance the signal has to travel. So the wider the distance, the longer it takes. That's just the the physics of it, the speed of light problem. The further apart things are, the longer it takes. I am, however, really impressed that the networks on the global networks operate as fast as they do. You can measure ping times from, let's say, where you are to some place that's on the complete opposite side of the globe. And then if you calculate that distance, you can use Google Maps or something like that to calculate the distance, the more or less the straight line distance between where you are and some other server, and then you work in the speed of light, it turns out the computer networks run at over half the speed of light. It was just like incredibly fast that it can get data around the planet that fast and go through all of that equipment along the way and still be not that much slower than light takes to actually just make the same journey. Really, really fast. Oh, Nunya says, I can definitely relate to your GPS story. That's happened to you, huh? Where it took you through a loop. Oh, yeah. Isn't that annoying when that happens? And you're kind of like at its mercy, right? Maybe you're in a part of town, or you're a part of the wherever you're traveling, you're not really familiar with, right? So it's kind of like you can't do anything. You can't say, oh, I know a better way to do it, because you might be in an unfamiliar area. I've certainly had the GPS suggest routes to me that were physically impossible. Like, turn down this road, and then it turns out that road has it's some back rural road. I go, I hope you're taking me down this road because we're going around some problem on the highway. And certainly it was. I looked at the map and saw, oh, there's an accident on the highway. That's why it's taking me down this road. But then like the road ends up like going nowhere. So I had to like turn around and go back to the main road and then find my way again. That happened not too long ago, maybe 5-6 years ago. I was traveling to, again, a place, but in an unfamiliar place, and I was going through all these back roads. I'm like, why are we doing this? Why are we not on the freeway? But it was really routing me around a problem that was on the freeway. So even though it seemed longer to me, it was probably shorter than it would have been if I had just stayed on the freeway.
Taking the back roads is also more scenic.
Well, that's true.
I'd rather go back roads over freeway, because the freeway is just like
Boring,
the same thing over and over again.
Boring cars, right?
Yeah, going through the back roads, you at least see some scenery or
Yeah.
some goats.
Some goats. Yeah, I would say I did enjoy going through those back roads, but it was still kind of unnerving a little bit. Like, where is it taking me? I hope I hope it's not totally confused, and I'm going to somewhere where I shouldn't be going. All right. So I think I'll finish off with one last application for shortest path algorithm. So you imagine a photograph. Let's say you have a photograph like this one here. And you want to resize this photograph. Let's say it's too big. You want to, crop it down so it's not quite so wide, or maybe not so tall. And so if you just use a naive resizing, where you just go into Photoshop and you say, make this thing narrower, what it will do is it will squeeze the image down. Everything will become distorted and everything will become thinner. And of course, you can look at this and go, well, the obvious thing to do is just take this stuff on the left-hand side and just crop it off. But, you could do that manually in Photoshop, but how could you just tell Photoshop, I want to make this photograph, let's say, 25% smaller, but retain the important information and throw away the unimportant information? And so this technique, called seam carving or context-aware resizing, was invented not that long ago. And it's really amazing when you see it in action. You can get these demonstrations of it on the internet. You just search for a seam carving demo and you come across websites like this. And so the idea here is you've got this photograph that has areas of high amounts of information and areas of low amounts of information. And so what this algorithm does is it converts the photograph into what it calls an energy map. An energy map is a, well, it looks like this picture down here. So areas with high amounts of detail, and the way it determines that is if you have two adjacent pixels and they have a very similar color, then we can say the energy of those pixels is low. And if those two pixels have a difference in color, we can say the energy of those pixels is higher. So it's basically finding areas of the image that have large changes in color information. Areas of the image that have not as much changing information have a lower energy. So each one of these pixels has been assigned a number based upon its difference in color from its neighbors. And then what this algorithm does is, since every pixel has been assigned a number, it finds the shortest path through that image, starting at the top and going to the bottom. It looks kind of like this. So let's say this is our array of pixels, and every pixel is connected to just its neighbors going downward. And there's two imaginary vertices, one at the top of the image and one at the bottom of the image. And the goal here is to start at the top and find the path through the image that has the lowest overall energy. So you're trying to minimize the energy. So, maybe it takes you in a zigzag pattern. So the idea here is you pass through each vertex, you go to the next vertex that has the lowest energy, and you find the shortest one overall, or the smallest one overall. And that's what this zigzag pattern is over here. That's this shortest path from top to bottom. Once you've identified all of the pixels that you pass through going from top to bottom, you're guaranteed by this algorithm to have selected no more than 1 pixel per row. All right, so you take a look at this picture again. As you work your way from top to bottom, you will select 1 pixel per row. And then you just remove those pixels from the image. And that shrinks your image down by 1 pixel. Then you repeat the process over again. Find the shortest path from top to bottom that has the lowest overall energy, and then remove those pixels. And do that over and over and over again, and it will shrink the image. Here's a demonstration of it. So watch this one over here. Down here in the lower right, you'll see what happens when you shrink the image just using a naive approach where you just compress everything. So you can see this castle is slowly sliding its way over to those people by removing the pixels that are in the middle. Now, eventually, that castle is going to get slid over all the way, and it'll have to start removing pixels from the castle itself, so things get distorted. Right? But you never really would shrink the image down by that much. Let's say you just wanted to remove 25% of the image. You end up with something like this. So all the information, the important information has been retained, and all the useless information or less useful information has been thrown away. And you can actually upload your own image to this. Let's upload that whale image. Let's go find that. You can do the same thing. All right, good enough. So it's retained the shape of that whale's fin, but it threw away, cropped out the less important information about that empty ocean off to the left-hand side. Pretty cool. Here's another demonstration. So let's say we want to make this half as wide and 70% as big. So this slides all those balloons closer together. more or less retaining their shapes and cropping out the uninteresting sky. And I think this demonstration is interesting because it says that we can also selectively erase these balloons. We can, let's say I want to erase this one, and I want to erase this one, and I want to erase this one. By giving them all the same color, we've essentially lowered the energy of those pixels, and it will remove those first. You can see, zip, that balloon goes away, and that one goes away, and that one goes away. Looks like lightning bolts eating it up. Pretty cool. And of course we can upload our own images to this. Let's do what happens to the scuba diving one? Now this one here is a challenge because we got all sorts of information going on here. So this may actually not be a good candidate for doing this algorithm too. But let's see what happens. And let's not try to shrink it so much. Let's go to maybe 80% and 80%. I don't know.
It's treating his legs as something that is low information.
Yeah, because it's mostly dark colors there, right?
Yeah. There's not a lot of color change or gradients there, so.
So his legs became a little deformed there, but
a little bit.
I wonder what it'll do to this one. Oh, it's not bad. Here's the original one. So as we mentioned, the it works well when you have images that have backgrounds that are more or less uniform, but it doesn't work well on images where the background has lots of changing information. So here, these backgrounds here are quite complex, and so the algorithm can't tell that the face is more important than the background, so it just kind of resizes it by cropping a whole bunch of stuff out, and the face ends up being skinny. Nevertheless, I think all of these websites that I just showed you use a JavaScript library that you can go and download and incorporate into your own websites. And applications like Photoshop already have this feature built in. In fact, I used it a couple of months ago when I had taken a group photo with my family, and it turned out a couple of us were standing a little too far apart, and so I used the resizing technique to basically move everyone closer together, because we were just standing against a featureless wall, and so I was able to move everyone closer together using this algorithm. I thought, there's an actual application for this in order to get everyone more scrunched together in a group. So there you go. There's another application of the shortest path algorithm. And I must say that things like image manipulation are just this ever evolving technology where people are coming up with better and better algorithms to do things that before had been impossible to do. I remember, again, this was maybe 5-6 years ago, I saw this video. Every year, Adobe puts on a a conference where developers can come and learn about some of the new technologies that they are incorporating or thinking about incorporating into future products. And so these researchers came on and showed an example of, well, I guess, I can't find the video right now, but basically the idea is, you got your camera, right? And you take a picture, and sometimes the picture comes out blurry because you were shaking the camera a little bit. Now, I must say, these days, the cameras in cell phones have one advantage over a standard camera, in that they have an accelerometer in them. So I've noticed that this phone here is pretty good at taking sharp pictures, because what it does is, as I'm holding the camera, and I'm jiggling it a little bit, the accelerometer is measuring the amount of jiggle. And then the moment when it detects that my phone is kind of like at rest, it takes the picture at that moment. Right? So it's measuring the amount of movement I'm making. And when I'm just stopping, it takes the moment when it knows that my camera's not moving. And so that's pretty good. But for, a standard camera, if you're moving the camera slightly, the picture comes out to be blurred. Everything's been smeared a little bit. And the common wisdom amongst photographers and digital animation and digital photography people is like, there's nothing you can do about that. When you smear the pixels, you're losing information. The pixels blend in with each other. And then here comes these researchers saying, we figured out a way to remove camera blur. And so they brought up a picture that was a little bit smeared, and then they ran this new filter, and then boom, it just sharpened up. And then like everyone's jaws in the room just went, how did you do that? Right? That is, we thought that was totally impossible. And these people said, like, well, we figured out a technique to basically unblur the pixels, unsmear them. I think they said something like, well, if we know that the camera is moving, we can calculate by looking at the pixels what direction the camera was moving in. And so all the pixels have essentially been smeared in that direction. And so all we have to do is just kind of like unsmear them back in the reverse direction. And then out comes, a relatively sharp picture. It doesn't have complete information, but it's much better than what we had before, which was nothing. And so I guess I just wanted to bring up that story because these sorts of things are coming out all the time. If you ever thought for even a moment that everything that has been invented has already been invented, that's just simply not true. New stuff is coming out all the time. There's plenty of open areas of research to try things that we've never seen before. My Facebook feed right now is, for some reason, I think they know that I'm a photographer. I see these ads for these plugins for Photoshop that can sharpen a photograph, that can basically take a blurry photograph, not blurry because it's smeared, but blurry because it's out of focus, and sharpen them up. Or blurry because the image has been shrunk down, right? So we've got a fewer number of pixels. Now we want to make it bigger again. You've probably seen this in movies all the time, right? They take some blurry photograph and then the superhero comes over and says, hey, enhance that photo. Zoom and enhance, right? So they make the picture bigger and then they click on this magic button that just brings back all the details. And, you can't really do that in real life, because if you have, let's say, an area with 9 pixels in it, you can't turn that into 100 pixels because you've only got 9 pixels worth of information. You can't figure out what the missing information was because it's just not there. But these new Photoshop filters can put information back. But the way they work is they don't actually figure out what was there originally. They figure out what could have been there. They've been trained by looking at hundreds or thousands or millions of photographs, both sharp and blurry, and they've learned that if you see this particular pattern of pixels, it probably means there was this other thing in the background. Like if you see this blur of green pixels, it probably means there was grass there or there was leaves there. And then it pastes back in what it thinks could have been there. And so when you look at the photograph, it seems completely plausible that that's what the photograph was. But in reality, there might have been something else there, or it might have been slightly different. Like there could have actually been leaves there, but it wasn't actually those leaves. It was maybe some different ones. Or when you see like you know, a blurred shot of someone's hair, it can go, oh, that's hair, so we'll just paste in like what it thinks the hair should have looked like. So it's not necessarily a replacement that reflects what the actual reality was. It's a plausible reimagination of what the reality could have been. And so it's all done now by artificial intelligence that analyzes the pixels and goes, oh, that looks like it was a brick wall, so we'll just put in the bricks. And so to us, it looks plausible, but it may not actually be reality. And so I guess the downside of this is, what if photographs like that get used as evidence in like a criminal court? You know, what if somebody has a security cam, you know, video, but it's got a little bit blurry, or the crime was being committed in the distance, and so there's not very many pixels of information, and so they essentially go enhance. They throw it into one of these filters, and the filter says, oh, here's what I think it should have looked like. You know, can you present that as evidence? Probably not. But who would know? Who would know that that's not the original picture? You know, there's always upsides and downsides in any technology. And so I think, you know, these sort of things have to be put to the test. Would you accept as evidence a photograph that has been sharpened using one of these artificial intelligence techniques? As for assignments this week, I do not have an assignment for you this week. You get a week off, in part because we have spring break, Easter break coming up. So next week there will be no live sessions. Then we'll resume on, what is that, April 18th, I think, Monday the 18th. And we will continue again talking a little bit more about graph algorithms. And then we'll start segueing into the next topic, which is finite state machines. So we'll be looking at new kinds of graphs and new kinds of information we can represent with them, and then stuff we can do with them. So before we take off, do we have any comments? Questions?
I can't think of any right now, but
So I guess the key takeaway here, the big picture is lots of problems that we need to solve lend themselves to representation as a graph, particularly problems that have like bases in reality, like you're doing mapping problems, of course, as a graph. But other kinds of problems can also be turned into graph problems. You know, one that just pops into mind is like resource allocation problems. You want to assign a certain set of resources to a certain set of things that are going to use those resources. And let's say there's a limited amount of resources. You know, one example might be you have, I don't know, a conference that you're going to. So you've got all these conference rooms, you have dozens of presentations going on simultaneously, but you maybe don't have enough microphones for everybody. So how do you allocate the resources to the people that need microphones, and how do you reschedule the presentations so that you maximize the use of the microphones, given the constraint that you don't have enough for everybody simultaneously? So you can do that with a graphing problem. You graph out the resources in some way. You graph out the consumers of those resources. You put in edges where consumers need resources, and then you do things like find paths through that algorithm or find groups. And that suggests to you ways that you can schedule the resources so that you maximize their usage while also taking into account that you have a constraint on them. So lots of problems can be transformed into graph algorithms. And then once you do that, sometimes the solution to solving that problem becomes more evident. So over the next few weeks, we're going to see things like how a computer program can be turned into a data structure, usually a tree, and then how we can use that tree to transform that program into another programming language. Also, how can we use those trees to do things like pattern recognition, looking for patterns. This is how compilers can tell the difference between a number versus a variable in your program, and how it can tell that this program is syntactically correct and this other program is not syntactically correct. Again, it's by applying patterns to it. Patterns can be things like, does this opening parentheses match up with another closing one somewhere else in the program? And do they come in the right nesting orders? Combining braces and parentheses, make sure that if you have an opening brace and then a parentheses, then the other side of it has to be a closing parentheses and then a closing brace. They can't be switched around. The order can't be switched around. So these, excuse me, these are the kinds of patterns that these compilers look for. And so we'll explore ways that we can use graphs in order to represent that information. Okay, so if we don't have any questions, then I think this would be a great point to end it. Actually, let me just really quickly make sure there's no lab assignment, but I believe there isn't. So I'm just going to go and check super quick. Give me a moment. Scrolling down, graphs. Yeah, we don't have any. So our next programming assignment is going to be coming up in a couple of weeks. And then that'll actually be our last one. So we've got one more assignment, one more programming assignment, and then we'll probably also have one more kind of pen and paper assignment that we have to do. And then that'll be it for the semester. So there we go. Well, I hope you all have a great rest of the day and enjoy your Easter break if you have one. And then I will see you in, what is that, 12 days.
Goodbye, Professor.
All right, bye-bye. Take care. Bye-bye. And YouTube folks, same thing. Of course, I'll be here tomorrow with my C programming course. I'm going to talk more about cracking passwords. But other than that, I will see you in 12 days. Next Monday. Not next Monday. Monday after next. Have a great day, everyone. I hope you have a wonderful rest of the day, and I will see you next time. Bye-bye.